Well, I think we're going to get started just in the interest of time here. Welcome, everybody. I'm Milo Christensen. I'm part of the Generosity team. This is the first in a series of forums that we're going to be doing this year. The first one today, then we're going to have another one next week, and then there'll be 3 more in the fall. And we're looking at this in terms of generosity. Generosity being caring of the earth. That's one aspect of generosity. And Linda Campbell, who's in the back there, was the person that came up with this idea. And she also did all the work, which was even best of all worlds. So anyway, we're very pleased to have our speaker this morning, Bill Middlecamp. And I'm going to read a short bio, and then I'm going to get out of here and sit down. Bill Middlecamp is a trained climate reality leader and is a trained En-ROADS ambassador. Bill has a BS degree in meteorology and an MS degree in computer science and is a commissioned United Methodist Earthkeeper. For more than a decade, Bill has participated in organizing and delivering dozens of presentations on environmental issues related to health, economics, science, and solutions to the harmful changes we are seeing. Bill is retired and dedicates himself to teaching about our degradation of the critical life-sustaining properties of the environment. Bill also serves as the director of the board of Dakota Electric Association, a rural electric cooperative. Bill, welcome to Elk River Lutheran Church.
Thank you. I'd like to begin with a prayer. Lord, I thank you for this gathering of believers who take to heart your commandment that we should be good stewards of this earth, this wonderful earth that you've created to support all life. And we recognize that responsibility. I appreciate that people have come with open minds and open hearts to hear your word, to learn and to serve you, God. Thank you. All right. Let's see if this is going to work. Come on. Well, there we go. All right. This is what we're going to cover in today's talk. It's a fairly long talk, and I can overspend the time, so I'm going to try to go through quickly. I say hold questions till the end, but I actually would prefer if you have a question, especially since I'm going to go really fast, that you interrupt me if something's not clear, and we'll talk about that. But the main points I want to make today is that the worldwide environmental energy balance is changing. What does that mean for humanity? What can we do about it? And what are the next steps? This is a little cartoon from Gary Larson. It's Grandma in the kitchen. There's everything's broken, stuff is laying all over, Grandma's laying on the floor, and the cookbook is called Recipes for Disaster. And that's really what I'm going to talk about today, is that the life we have, the wonderful things that we enjoy through the abundant availability of energy, and what that has done for society is wonderful, but we're cooking from a cookbook that is a recipe for disaster. It's not sustainable. All right. First of all, I want to make clear that almost all the energy we have on Earth comes from the sun. I've seen charts where the comparison of all the energy that humans create from burning fossil fuels, from nuclear energy, and all other sources of energy is a very small fraction of the constant flow of energy coming from the sun. Something like 90 minutes worth of sunlight on the Earth equals all the energy that humans generate and use throughout a whole year. 90 minutes. Well, what does that mean? So sunlight is streaming in from the sun. It heats the Earth gets warmer, and then the Earth radiates that energy back out into space. It's like being in a stream on an island, and you're watching the water flow through. It's coming in from the sun, streaming past the island, and streaming away. Now, the water level around the island is a function of how much resistance there is to the flow of that energy or that water. The temperature of the Earth is a function of the resistance of the flow of energy from the sun onto the earth and then back out into space. This is basic physics. If you take a look at Earth as a solid rock with no atmosphere, the average temperature of the Earth would be 0 degrees Fahrenheit. Think about that. Frozen. We'd be an ice ball if you had no atmosphere. But the atmosphere provides resistance, kind of like a dam in that stream, provides resistance to the flow of energy. If all the energy came to Earth and just stayed here, eventually we'd be the temperature of the sun. Not good. But it doesn't stay here. It tries to escape back out to space, but because of that dam of against the flow of energy, that greenhouse gases in the atmosphere, we actually see the temperature average being about 57 or 58 degrees Fahrenheit. Imagine a beaver in the stream putting logs down and building a dam and building a reservoir behind the dam, right? The higher the beaver builds that dam, the more water there is in the back of that, behind the dam in the reservoir. It's the same thing with greenhouse gases on Earth. The more greenhouse gases we have, the higher the temperature rises. It's just that simple. What happens is the sunlight coming in is high frequency because the temperature and the frequency of light are related, and the sun is very hot, so we have high frequency energy coming in, short wavelengths. It doesn't interact with the atmosphere very much at all. It's like a clear window. The energy streams in, hits the Earth, warms the Earth. Now because the Earth is much cooler than the sun, the energy flowing out is long wavelengths, infrared. And those long wavelengths, they interact with molecules in the atmosphere. In particular, carbon dioxide, methane, nitrous oxides, and the so-called F gases, which are manufactured gases that we use in solvents and refrigerants and so on. In 1856, this woman, Eunice Foote, discovered this effect. She just took bottles of carbon dioxide and other atmospheric gases, and she set them out in the sun, and she noticed that the bottle filled with carbon dioxide was warming. All right, so what does that mean? Over the last 12,000 years, we've seen the temperature, I don't think this will show up. Yeah, it doesn't usually show up on screens. But what we see here is that 12,000 years ago, we were coming out of an ice age, and the temperature was rising. The temperature marks here is 1 degree negative and 1 degree positive Celsius. That's 1.8 degrees Fahrenheit. But you can see it's not a very wide spread here, but the temperature was coming up, and it hit this 0 mark, which is kind of an average of what the temperature has been over a very long period of time. The temperature rose and stabilized about 8,000 years ago. And if you think about that, that's about the time, that's as old as some of the oldest records we have of human civilization. Human beings, modern humans, have been around, nobody's quite sure, but certainly 100,000 years, probably 300,000 years, maybe as much as 1 million years. But it's only been in the last 8,000 years that we've built societies and built our wealth on a very stable climate. Think about that. We lived in the trees, we survived, we barely survived in this period of less stability. And then as things stabilized and we could count on the environment to support an agricultural lifestyle, we started building things like pyramids and the things that we can find around the world, the oldest of which are about 8,000 years old. Well, we are leaving this stability behind, and we don't know where we're going. This is a 2,000-year chart. So this is about the time of Christ. And again, you can see that the temperature has been very, very stable. Again, the range here is now even smaller, half a degree minus to half a degree to 1 degree plus. And what you can see here is that we were starting to slide into another ice age until about 200 years ago when we started burning fossil fuels in great quantities to power our society. And now we are continuing to accelerate the burning of fossil fuels. We're not burning less, we're burning more each year. And we're pushing ourselves into a new realm that we don't know. We don't have any experience. We can't really predict what's going to happen here. Scientists have a good idea because they understand the processes at work, but how that actually plays out in our society is largely unknown. This is another way of looking at the temperature change. And what you have here is kind of like a clock where the months of the year, January, February, March through December, every time you go around this, it's 1 year. This is going to start in 1880 and it's going to finish in, I think, 2020 or 20-something. Anyway, the green is the average temperature from 1950 to 1980, a 30-year average. This is 1 degree cooler Celsius, 1 degree warmer Celsius. And I want you to watch. The white is the average. Blue is colder, and red is warmer. And you'll see there's variation from year to year, but it's pretty stable. It's pretty close to that zero line. What you're going to see here, though, as you get into the 1980 time frame, it's going to start getting red, and it's going to start going outward more and more. As you can see, there's very little variation. We did have some red in particular. I think that was like the Dust Bowl era. But here we come into the 70s. We're going to start seeing those circles getting farther and farther out. And when this is done, it's going to tilt it on the side so you can see it in more of a time frame. As it tilts, what you'll see is that from the period from 1880 to 1980 is pretty much straight. And then in 1980, it starts going out like this. This is not a short-term trend. This is 40 years, right? This looks like a water tower. It's really clear we've changed and we're going in one direction, and that's toward warmer and warmer environments. This is another way of looking at temperature anomalies. And this is a bell curve, or a so-called Gaussian curve. And along the bottom here are standard deviations. Now, the statistical models, the mathematics of statistics, say that within 3 standard deviations, you have 99.7% of all the samples. So there's only 0.3 or 3 thousandths that are outside of 3 standard deviations, right? Now, watch what happens as we start in 1950. And you see some variation, of course. These are 10-year averages. And then things just start dramatically moving to the right. Remember, above 3 standard deviations, you're only supposed to have 1.5 thousandths. 1.5 here, 1.5 here. We still have cold. We still have warm extremes. But fewer and fewer cold extremes, more and more warm extremes. This is the data, all right? This is not a hypothesis. This is data. Here's another way of measuring things changing. This is the Keeling curve. It's the recording of carbon dioxide in our environment. Carbon dioxide is a very strong greenhouse gas. And it's been measured consistently since the late 1950s. I think about 1958. And what you see here, this little sawtooth pattern, those are seasonal variations. In the summer in the northern hemisphere, we have lower carbon dioxide because things are growing and they absorb carbon dioxide. In the winter, they die and they release the carbon dioxide. And there's more land mass in the northern hemisphere. So these show you the troughs are the northern hemisphere summers, the peaks are the northern hemisphere winters, but it's very consistent, up and down, up and down. But this trend of growing and growing, and I put this red line in here to show you, this is a straight line, the red line, but the curve is not straight. It's accelerating, right? One of the things that I like to point out about this chart is you'll hear people say, and this is disinformation, people will say that volcanoes put out more carbon dioxide than all of the activities of humans, and by a large margin. Well, you remember Mount Pinatubo in the Philippines when it exploded? It was a big explosion. It had worldwide effects. Can you find it on here? I can't. It actually is 1%. Volcanoes put out 1% of what humans put out. So, we are,
Bill, quick question for you. All the data and the graphics that we've just been looking at, as well as, I'll call it the clock, and the shifting bell curve, are those available someplace for us to be able to look at those again?
all of these are public sources, and a good place to start is nasa.gov. They've got a whole range of information about climate and what they're measuring, and they share a lot of the data. That clock, if you search for GIS temp, GIS temp, I don't know if I put it on the chart, on the notes, but I have a bunch of references on the notes, including the ones for NASA. GIS temp is that animation of the water tower slide.
Thank you.
And I actually have here keelingcurve.ucsd, University of California, San Diego.edu. All right, so for 8,000 years, the inflow of energy past that island in the stream has been balanced with the outflow. And now we're raising that dam. We're like beavers. We're adding to the size of that dam, and we're increasing the temperature of the Earth. Since 1980, the outflow is measurably less than the inflow. And we're going to continue that until we reach a new equilibrium, but because we're moving the goalpost, as I said, we're accelerating how much carbon we're burning, and it's just accumulating more and more in the atmosphere, so we're moving the goalpost. What does it mean for humanity? Here's another cartoon. It says, "This is it, Jenkins. Indisputable proof that the Ice Age caught these people completely off guard." And here's Ugg. He's looking out at the outhouse. His club is sitting outside, and he's wondering, what the heck? Well, we're not caught off guard. We have good science. We know what's going on. But what does it mean? Oh, you all know the story of Corey Stringer. Stringer or Springer? Stringer. Corey Stringer is a Viking football player who died at a practice in Mankato. It wasn't particularly hot that day, but it was very humid. And he passed out. They called the ambulance. He got up. He walked to the ambulance. They took him to the hospital. They did everything they could to try and save him, and he still died. This is kind of the nature of heat-related deaths. Heat-related deaths are the highest cause of death from weather-related phenomena. Humidity is an important thing to pay attention to. You know, what do you think is the temperature that we can survive, the highest temperature, if the air is dry? You know, people go out to they live out in Sun City and they say, well, it's a dry heat. It's hot, but it's a dry heat, right? Well, what's the highest temperature that people can survive for more than 6 hours if it's dry heat? Do you have any idea? It's about 124 degrees. But what if it's 100% humid? What's the highest temperature? This is called the dew point, by the way.
75.
It's not a bad guess, but we have hit 75. In fact, a couple of weeks ago, it was 78 here in Minnesota. It's actually about 94. And the reason is because we cool our bodies with sweat, and that sweat evaporates, and that carries away moisture. But when you have 100% humidity, that moisture stops evaporating, and we don't have a way to cool our bodies. So every human body is burning about 100 watts continuously. Imagine a 100-watt bulb inside your body, and your body has to get rid of that heat. When you can't get rid of that heat, you can't survive. So imagine if we get to the point where the dew point is in the 90s, those are places people can't live. And when you can't live someplace for even one day out of a decade, you're not going to live there at all, right? You're not going to just wait like Russian roulette for that day to come and then everybody's going to die. So they're going to move. And what happens when people move? You start to immigrate to other countries. You start to get a rise of protectionism. You start to get the rise of fascist governments. There's a very good essay by Thomas Friedman, economist, I believe, he believes that the war in Syria was caused by climate change. The farmers in Syria lost their ability to raise crops, couldn't support themselves, so they moved to the city. People started to react. They didn't like all these people coming in and changing their environment. So they started mistreating the farmers, and then conflict broke out, and that spiraled into a civil war. I will point out that a couple of election cycles ago in St. Cloud, Thomas Emmer was talking to his constituents, and they said, we want a moratorium on Somali immigrants, I think it was. And he said, well, to his credit, he said, I don't think that's constitutional. And they said, you don't understand. We want a moratorium. It's like people get wiggy when they see their environment changing. This is Paradise, Florida. One of the strongest correlations between climate change and changing situation around how this is impacting humans is that we're seeing more and longer and more destructive fires in the wildfire season out west. Now the fires are moving into towns, and basically the whole town of Paradise burned.
Bill, would that have to do with the fires in Canada too?
The fires in Canada are also related to climate change, and a large part of what's going on there is the warmer environment allows the pine bark beetle to survive winters. The pine bark beetle's killing huge swaths of forest, and then those forests are sitting there waiting for an opportunity to burn. That's a big part of it. But what happens in the wildfire season is that we have these, as the temperature warms, more water evaporates from the oceans and the lakes and so on. And moist air is the fuel for storms, for weather. It's like gasoline to the engine that is our environment, our climate, our weather. So you'll get these so-called atmospheric rivers that come off the Pacific Ocean into the West Coast, and that produces a lot of growth from the water. That growth shoots up and then dries out. And then that's fuel. You have more growth providing more fuel, and then you have these dry seasons, and then you have these fires. This is surface temperatures, and just to show you some extremes, this is actually from 2021, so it's already 3 years old. But what you see here is where, remember I said you could survive up to about 124? Temperature exceeded 50 degrees Fahrenheit, Celsius, 122 degrees Fahrenheit in at least 4 countries in that year. And we saw this year temperature extremes over 124. Think about that. That's a temperature that if you can't get out of that heat and into air conditioning, you will die. Here's Portland, Oregon in 2021. We had this massive heat dome, just an atmospheric phenomenon that happened over the Northwest. Portland is a place where very few people, at least in the past, have had air conditioning because they really didn't need it. It was a temperate, moderate climate. Reached 116 degrees Fahrenheit in Portland. And here in Seattle, similarly, 108 degrees Fahrenheit. This year, in the Gulf, the Persian Gulf, there were dew points that exceeded that survivable temperature. That's unprecedented. Hurricanes, again, the fuel for hurricanes is warm, moist air. The oceans are warmer. The temperatures in the Atlantic or off the coast of Florida this year, I believe they reached 90 degrees. So that's pumping a lot of moisture into the air, and then that's causing these hurricanes to rapidly escalate. They're called bomb hurricanes or bomb cyclones. And that refers to how quickly they grow from maybe a category 3 to a category 5 as they move across warm water. These hurricanes also are not moving as fast as they used to. They stall sometimes, and that again is related to climate change. And it has to do with the temperature gradient, the temperature difference from north to south or south to north. The more that temperature gradient is another factor in weather. And as you diminish that gradient, you have storms stalling out like that heat dome, and you have things like the loopiness of the polar vortex. These are things that are caused by a different environment, again, an environment that we're not used to and we don't fully understand. This is Argentina, and that is hail. This one I particularly touches me. Who's coming to save us, when our fire trucks are floating? You might remember in 2021 there were quite a lot of floods, heavy floods in the southeast. This is Tennessee. And what's particularly concerning, especially for Christians, and as I understand you talked about today, that we're meant to serve and we're meant to love our neighbors, right? We're having an effect on Africa where extended droughts are causing it to be impossible to raise food. And again, those people are leaving. Some of them, parents are leaving their children behind and moving to where, looking for work. And when you get these large influx of immigrants, even into countries that have been very welcoming of immigrants, when it reaches a certain threshold, people say, stop. How do you stop people who can't survive? They've got nothing to lose. They've got to move. I want to point out here, this is Minnesota, and you can see that this is a measure of soil moisture, and we become drier. This is by the end of the century, 2095. We're going to be like down here at the end of the century. Now what's interesting is we're actually getting more rain than we used to because there's more moisture in the air and we have more storms, but we're also getting a lot hotter and that moisture evaporates. So the net effect is that it's drier. What can we do about it? Well, first of all, we have to be very open, eyes wide open about what are the things that we're doing that are causing the buildup of these greenhouse gases. And as you can see, it's all over society. There are even some sources that are natural ones, but they are being triggered by the warming that we're causing. So as the permafrost in the north warms, and one of the effects of climate change is that it has more effect at the extremes. It has more effect north and south poles. It has more effect at night. It has more effect in the winter. It's not so much in the summer that we see the effects of climate change. It's that, that heat takes longer. It's like having a blanket on you. So the heat takes longer to leave at night, so nighttime temperatures are warmer. It doesn't leave as readily, as easily from the poles, so they warm up. And the melting of the permafrost is now releasing eons worth of stored carbon. There's a cave up in Alaska where people can go down and they can explore the permafrost, right? And they say it smells like gym socks in there because of all that stuff that's waking up and starting to decay. And as we melt the permafrost, we're triggering the release of methane because as that stuff decays anaerobically, it turns into methane, and that methane is a stronger greenhouse gas than carbon dioxide. So we've got to hurry. We can't wait for this to be a problem because when these so-called tipping points happen, where nature starts to contribute to the problem, we can't turn that off. All right, so where do we produce greenhouse gases? This pie chart shows you that transportation is the largest source. Electric power used to be the largest, but it's because of things like wind turbines and solar, we've actually reduced that. Also the conversion from burning coal to burning gas. Gas produces about half as much carbon dioxide as coal does. It's still a problem, but it's better than coal. So we're seeing this declining. We're seeing these others grow proportionally. Behind transportation, and this is all kinds of transportation, cars, trucks, planes, boats, everything. Industry, making cement, making steel, making anything uses a lot of power. Then there's commercial and residential, our buildings. They actually are a very large component, and there's a lot of low-hanging fruit there that we can do, and that's some of the things that I'm going to be talking about that you might do. And then the way we do agriculture, and this includes cutting down trees to make paper, changing the nature of forests so that affects their ability to store carbon, because growing things store carbon. Now I'm going to shift into what's kind of a solutions calculator, right? This En-ROADS is a system dynamics model where it's kind of like a spreadsheet. Have you ever done a spreadsheet where like you were trying to figure out what your mortgage payment or your car payment was going to be, right? You build in all these formulas and then you can just change one parameter and you can see the effects ripple through. That's kind of what En-ROADS is like. It's a very complex tool that takes into account economics, takes into account climate and weather. It includes a lot of different disciplines, including, for instance, how long it takes to change society. When you develop a new technology, how long does it take for that technology to ramp up? There's something called the S-curve of development where you have a slow growth of a new technology and then you have a rapid period of growth and then it peters out and you've played out all the advantage you get out of that technology. That S-curve, it grows at kind of a constant exponential rate, but because it starts from very low numbers, it takes a long time before it starts to take off. And that's built into this model. So you can't snap your fingers and say, okay, we're going to turn all of our electric generation from fossil fuels into nuclear. It just doesn't happen overnight. It does about 14,000 calculations every time you change a parameter, and there are a lot of parameters you can play with. It doesn't predict what's going to happen because we don't know what humans are going to do, and that's not part of the model. But it does take into account that if we get humans to do this thing, then this is likely what's going to happen. And it's really good for adjusting assumptions. So you've probably heard about how if we planted 1 trillion trees, we'd solve the climate problem. Well, you can ask that question in En-ROADS and see exactly how much of an impact that has. It's free and easy to use, and it's constantly being updated. So this is what it looks like. Over here you have the energy, and that's brown is coal, red is oil, blue is natural gas, green is renewable energies, wind and solar and so on. This, I don't know, what color is that? It's sort of a purplish, that's bioenergy, burning wood, ethanol from corn, that's bioenergy. There's nuclear on here, you can barely see it, it's a blue or a teal sliver. And then this new zero energy, this could be fusion. You've heard about hydrogen fusion being a new source of energy for the future, but we haven't invented it yet. We haven't successfully used it to generate energy that we can actually deliver to homes. But what if we did? You could play with that. So you change these sliders, and then you see how that changes where we get the energy from. There's a whole lot of graphs that you can choose from. This is just one example. And then over here on the right, you have the results. And again, there's a lot of different ways you can look at the results. This one happens to be the greenhouse gas emissions, all right? And as you can see, the greenhouse gas emissions are still rising year to year. We haven't turned the curve around. We need to turn that around, and we need to go negative and actually take some carbon out of the atmosphere. The black line is the status quo. If we don't make any changes, this is where we expect we're going to end up. And the blue line is what happens when you make the changes, when you adjust the sliders. So you can see how much of an effect it has and when it has an effect. And then over here on the far right is an estimate of the temperature at the end of the century. Now you've all heard about the Paris Accord, which said we want to set a limit of the increase in global average temperature to 2 degrees Celsius, 3.8 degrees Fahrenheit. Then they came back after making that agreement and said, well, what happens if we stopped at 1.5 degrees? And they came to realize that the difference between 1.5 and 2 was really large. And there were some areas of society, in particular the Pacific Islanders, who said, If you go all the way to 2, we're done. Our islands are going to be underwater, right? So we're going to try and get that down to 1.5 or better. And so in the middle here, talk some more about the sliders. These are the ways we use energy. And it includes transportation. You know, what if we make it more efficient? You know, everybody drives a Prius. Or what if we electrify it? Everybody drives a Tesla. Buildings, what if we make them more energy efficient and get their source of energy from electricity? And then down here at the bottom, there aren't ways that we use energy particularly, but they do have an effect on it, and that is population. What if we have a lot more people or a lot fewer people, growth, and then economic growth as well. And then over here are some ways that we can control the carbon dioxide going in and other greenhouse gases. This one is deforestation and afforestation, planting trees. And this actually is an older slide, so the new En-ROADS has changed already. And if you look at it today, you'll see that these have changed. But these are other greenhouse gases, methane and the so-called F gases, and technological means such as carbon capture and storage. So I've gone through and I've made a few examples. What if we have a moonshot program where we go all in on nuclear, all right? And what you see is that that teal color has grown a bit, but it is a very small fraction of all the energy we use. And this is all the energy. This is not just energy that we use for generating electricity, but nuclear is pretty much limited in its use to just electric, right? So you can see we still use a lot of coal and oil and natural gas. How about if we push real hard on renewables and that green area gets a lot bigger? And in particular, I didn't just say renewables, but I also said carbon price. Now what this is it's a solution that economists love. And it is basically you start at wherever the energy comes from, the mine, the wellhead, and you put a fee on that. And you say, okay, for every ton of carbon, we're going to charge maybe $10. You start at a low number, and then you gradually grow it over time so that there's constant increasing pressure to move people away from solutions to modern day life, appliances, devices, whatever, toward ones that use less carbon, all right? Now what's cool about this is you get to make your own choices. Nobody tells you you can't drive a gas car. Nobody tells you can't take a vacation. You can't use electricity to heat, whatever. You get to choose in the marketplace. But that market force of trying to find the best price for the products that do what you want to do is going to steer you in the direction we want to go. Now the other side of this is, what do you do with all the money that raises? And this is very important. You turn that around, and instead of using it on government programs, you give it back to the citizens in equal amounts. So I get 1,000, Bill Gates gets 1,000. It means a lot to me. It doesn't mean so much to him. So it tends to help people at the lower end of society who, by the way, use less carbon anyway. And so they can actually come out ahead because they can take that money and they can use it to offset the rising costs of fossil fuels if they must use fossil fuels, or they can use it to buy new products in the market that save them money because they're cleaner. They don't produce greenhouse gases. And as you can see here, there's a period of rapid change and then it sort of peters out, levels off. So that by itself is not a solution. And what we see here is at the end of the century, 2.6 degrees. That is a good result, but it's not enough. All right, make cars and planes and trains more efficient, but electrify them as well. And what I want to point out is that you can see we haven't changed the sources of energy enough, so we need to also take a carbon price, or we need to somehow move people toward cleaner sources of energy. All right, here's one, make buildings more energy efficient and electrify them. How about controlling methane and other gases? It's actually quite a lot. When you recycle your refrigerator, make sure it's recycled responsibly and that we don't release those gases back into the atmosphere. This is carbon removal technology, carbon capture and sequestration, or direct air capture, DAC, direct air capture. Machines that, yes?
What about the batteries that the electric cars use? They're only supposed to last so long and then they get recycled, is that?
Good question. So we have to spend money and resources to build new products that, are going to help with climate change, right? And if we choose something that has a big impact on the environment, will it make it worse or will it make it better? So we have to look at the total energy and materials that are used in a gas car and compare that to the total energy life cycle of materials that are used in electric cars and cleaner cars. And what we know is that the extra carbon and energy that goes into making an electric car is recovered in about a year and a half. So it's actually quite quick, and then that car is much cleaner going forward. And that's based on the current sources of electricity. And as we make electricity cleaner, they get better. Now, how long do those batteries last? They actually outlast the cars. So the expectation is that they'll last 15 to 20 years. You won't have to buy a new battery. Your car's going to rust out, especially in Minnesota, before you need a new battery. And when the battery has diminished in capacity compared to when it was new, down to about 70% of its new value, it's not really useful in an electric car anymore, but then you can take that battery, which still has 70% of its capacity, and you can use it in a stationary application, such as for the electric grid, to help stabilize the electric grid as we move to more and more renewable energy, or in a home. Now, at the end of the total usefulness of that battery, they are very recyclable. And so the amount of resources that we take from the earth in order to build these batteries will sort of peter off over time as we get a bigger and bigger pool of batteries that can be recycled. Today, we're not doing any recycling, or very little recycling, because we're not getting the batteries back yet. Electric cars have not been in the market long enough to have a large stream of batteries coming back to use for electric system or for recycling. But when we do, I assure you, we will recycle them, because the value of the minerals that are in the batteries is far too great. Does that help?
Yeah, thank you.
All right, so here's where I just kind of put the pedal to the metal across the whole board. And so I put the carbon price up to the max and I left everything else alone. So no taxes on fossil fuels, no prohibition on fossil fuels. You can still use them if you want, it just costs you more. Maximize energy efficiency and maximize the electrification of, it's called beneficial electrification, to take energy from electricity that's clean rather than from fossil fuels like propane, natural gas, oil, gasoline. Substantially decrease the deforestation that's going on. Substantially increase the amount of planting new trees and managing forests to maximize their uptake of carbon dioxide. Carefully control methane and other gases and build these technology solutions to pull carbon out of the air. And what you see is now this graph is actually temperature change. And there's the 1.5 degree target, and here's the 2 degree target. As you can see, we're not going to be able, it's very unlikely, in fact, we're almost there, where the average temperature of the Earth is 1.5 degrees warmer than the pre-industrial average. So we're going to cross that line, but if we could do all these things, and that's a big ask, we would stay clear of the 2 degree line, and we would actually turn the curve around and start to bring the temperature down to what it was before we started making all these changes. All right, what's next? First of all, there are a lot of solutions that are out there, and I know that you've used some of them. How many of you have changed your light bulbs in your house to LEDs, right? Is that a sacrifice? No. It's not, is it? It actually saves money. It saves about 84% of the energy you put into lighting. It's a huge advantage. Light's light. Why do we care if we get it from inefficient incandescent bulbs? But people made a big stink about that for a while, that they felt like their freedom was being taken away. And so, if you, as a citizen who's concerned and recognize your stewardship responsibilities, demonstrate for other people that these solutions are not a sacrifice, they're actually better. I drove here today in my electric car. I can tell you there are a lot of advantages to electric cars. Not for everybody, but for me it surely works out very well. So talk about what you've done, enjoy the things that you've done, and talk about them and expect more innovation to provide even more solutions. You may have lowered the temperature in the winter and raised the temperature in the summer for heating and air conditioning. Travel more effectively. Reduce the number of trips you take, make them more efficient. Maybe take somebody along with you. A lot of low-hanging fruit there. Start to move away from fossil fuels now so that you're ready for the inevitable future. And the most important thing of all is talk about it. I want to talk about how I don't believe this can be solved by asking people to make sacrifices. We need to see these solutions as attractive and being something you want to go to. There's an experiment that was done by psychologists where they asked people to do something altruistic, and they had a control group where they didn't ask them to do anything, and they offered both of those groups a plate of cookies. The people who did something altruistic took more cookies. We have a psychology that when we do something that we consider to be good, we kind of expect a reward. People who use reusable bags and take them to the grocery store religiously tend to put more goodies in the bag. It's the same thing. We expect a reward. So if we expect to solve this by asking people to make sacrifices, they'll make sacrifices for a little while, but then they'll typically stop, and they may do something that offsets the benefits of the sacrifice they made. And I just don't think that we can convince everybody in society to do the things we need to do simply out of the goodness of their hearts. We need to have solutions that are attractive. And there are a lot of attractive solutions out there. So learn about them, talk about them, and tell people you're concerned, but you're happy to be able to do X, Y, Z, whatever. That's the end of my talk. Questions? Yes?
Bill, thank you very much for giving us this presentation, great presentation. I actually have two questions, but I'll just start with one so I don't take up everybody's time. I've done a lot of reading that right now there's different, I'll call it demography bombs going off around the world, which is basically there's not replacement generations in place for some of the older segments of the population. Even in India, they're projecting to drop below the 2.2 replacement birth rate. How do you see that decline in, if you agree with the decline in population, how do you see that affecting our future, I guess?
Well, you might have noticed when I showed you the chart that had all the sliders that I had actually maximized population and I had maximized economic growth. And what, if we were doing this dynamically, I could show you that moving those sliders doesn't have much of an effect on the climate when you've decarbonized society. So it becomes an issue all of its own on an independent, axis, if you will. There are a lot of reasons why population of the Earth is an issue that is its own issue, but we can separate that from climate change if we decarbonize our society. So it isn't necessarily, those two things are big arguments that people make. In particular, some Christians will say that this is anti-Christ, that this is, we're told to be fruitful and multiply, and to solve climate change, you want to, cut down on the human population. Sorry about that. That isn't true. There are people who will say that fixing the environment will kill the economy. That isn't true. It's actually the opposite. There's a correlation between every degree of warming, 2.5% degradation in global GDP. So it costs money not to solve the problem. Yes?
There's been some talk about solar shields in space to screen the Earth. Any thoughts at practicality and the effectiveness of the pros and cons?
Right. So the question is, what about doing something like putting big mirrors up in space to deflect the energy before it comes to the Earth. That's part of a whole category called geoengineering. A lot of different solutions. The practicality of building those mirrors in space is pretty ridiculous. They'd be very, very expensive. But that being aside, I mean, imagine you could do that. What effect would it have on the globe? Well, it isn't the same thing as not having the greenhouse gases. You change the distribution of energy across the globe, and you might change things, for example, like the monsoon seasons, where all of a sudden the monsoons are not happening, or they're coming too much, or they're happening at different times of the year. And what's important about that 8,000 years of stability is that during that period, we have figured out all the places around the globe where we can live. We live on the margin of where the climate allows us to grow the food we need and to survive. And we're going to roll the dice and see what happens on these geoengineering solutions. We don't know the effect. Clearly, you would reduce the amount of energy coming in, but that's one parameter out of many that go into how our climate works. Other solutions that are actually more practical and possible, one of them is to produce sulfide particles the way volcanoes do. When a volcano explodes, it puts a lot of sulfur high up into the atmosphere, and that shields the Earth from some sunlight for a period of up to about 3 years. And we can see the effect that that has. So what if we had a fleet of airplanes that was constantly spewing these particles into the high atmosphere? What would that do? Well, for one thing, it would produce a lot more acid rain, right? It actually takes us back to the 60s when we had a lot of those particles coming out of power plants. We've now put scrubbers on to take the sulfur out of the smoke. But we know what was happening. We know that forests were dying. We saw effects of that, and we can guarantee that bad things will happen. It'll cause more acidification of the ocean. That changes the environment of the ocean. It changes the sea life. I mean, it's just, and then if we go down the road of doing something with geoengineering and then realize, oops, that was a mistake, and now we stop, we've accumulated all those greenhouse gases, and they come back with a vengeance. And now what do we do? So the best thing to do is to cut down and try to eliminate the sources of greenhouse gases. That's far cheaper than these other solutions. It is the cheapest thing we can do. Yes?
Could you speak to hydrogen for transportation compared to the electric that still needs the hydrocarbons to make the electric?
So what about using hydrogen instead of electricity in cars? Hydrogen, when it burns, it mixes with oxygen and produces water. So that's pretty clean. No greenhouse gases there to speak of. So isn't that a better solution? Well, first of all, almost all the hydrogen we get today comes from what's called steam reformation, where they take methane, which has a lot of carbon in it, they get the hydrogen out of it, and then they release the carbon. So right now, today, the hydrogen we have is not clean. There's a lot of ways they talk about hydrogen, and there's gray hydrogen, and there's green hydrogen, and blue hydrogen, and all these different ways that you can get hydrogen. And one of them that, in theory, would be very clean is to take electricity and use something called hydrolysis, where the electricity causes the water molecules, H2O, to separate into hydrogen and oxygen. The problem with that is the process for doing that is not particularly efficient. And then when you turn around and you use that hydrogen, either burning it as an alternative to methane or in a fuel cell, which is more efficient, you still end up using about 4 units of energy in to get 1 unit of energy out.
But the energy that goes in can come off this product.
Yes, yes. So you can generate that energy cleanly, and so then you're not paying for the energy because it's free. It comes from the wind. It comes from the sun. But you're still taking 4 units of energy that could be used to offset carbon sources of energy elsewhere in society. So what is the effect of using it to charge batteries in electric cars? You get about 85% of what you put in comes out and actually drives the wheels going down the road. So if you, as a consumer, are looking at a car that's powered with hydrogen versus one that's powered with just electricity and batteries, you're going to pay probably triple for that hydrogen. And so in a market where people are making their own choices, they're not going to choose hydrogen because it's going to be a lot more expensive.
That's triple in this economy, but the hydrogen will be able to be used better for your semi-truck, your locomotive, pickup trucks,
Yep.
a lot of things that electric is not
Yep.
going to do.
There are definitely places where batteries don't work. Airlines are one of them, and that's where hydrogen is going to be a useful thing. And I think the best is a hybrid system where you build enough renewable energy to provide all the energy you need, carbon-free, but then you've got a lot of excess energy a lot of the time. And you take that excess energy, which otherwise would be wasted, and you use it to generate hydrogen. And then you use it for all the things that you can't use batteries for.
One last comment.
Yeah.
We drove out of Becker along the East River Road.
Right.
And they have hundreds of acres of the photovoltaic
Yep.
panels
Yep.
on prime farmland. That bothers me.
It bothers a lot of people. I will agree with you there that people feel like we shouldn't be taking prime farmland to put up solar panels. Here's the problem. Here's another look at it. I'm not saying that it's a problem. Here's another look at it. If you take an acre of land and you grow corn on it, and you convert that corn into ethanol, and you put that into a car, and you drive the car on that energy, you can go about 10,000 miles per year. If you take that acre and you put solar panels on it, and you use that in an electric car, you can drive more than 500,000 miles.
But also take that corn and feed the hungry.
So we actually convert 1 million acres of prime farmland to urban every year. We are using that land in ways that are not producing food. And, you know, there's a lot of things society could do smarter. But I think that the effects of not getting clean energy are very detrimental. And I think we could have a debate on this, and I'd love to have a debate with you about it, because I understand how important prime farmland is. But if you're a farmer and you have an option to plant solar cells and use that as a cash crop, and it turns out to be more valuable than growing other things on that land, isn't that your choice as a farmer? I mean, it's free market, right? The farmer should be able to decide what they do with their land.
But in society, there needs to be a balance. Through the farmers, I don't have a problem with them making money. But there's a lot of grass land that isn't viable for good crops.
There's another thing.
I believe we'll continue the question. Just want to thank everybody for being here. Tell your friends, tell your relatives. If you have another one next week, please come and join us. And we're going to be looking at what it means as Christians, what this whole idea of generosity toward and caring of the earth. So please join us next week, and thank you for coming.
Thank you. Thank you. Thank you. I wanted to add one more thing about that. There's a new movement, I guess, called agrivoltaics, where they combine agriculture and solar panels. And they have, for example, grazing of sheep and livestock underneath the panels, and they can grow some crops that don't like full sunlight. They can grow them under the panels very well. In particular, food crops, I mean, where we directly eat those products instead of, you know, like grains that we have to process.
When you drive home today, look at how much their land is on the highway.
Oh yeah, we could do that. That would be cool. Yeah.
No, but use that resource.
You should get Mr. Emmer on that.
Thank you.
Thank you, thank you, thank you.